everyone knows what I look like. Hello. So as Brian said, it is being recorded, so we all need to be on our best behavior, I would suppose. Okay, good. So this is going to be a super quick introduction to the idea of naive Bayesian classification algorithms and probability models. So coming out of this, hopefully you'll have the big ideas that relate to this particular topic. Audio is pretty scrambled. Let me adjust. Is that a little better?
Yes.
Okay, terrific. Thank you. Right, so as I was saying, hopefully this will give you an overview of and sort of a taste of naive Bayesian identifiers and classifiers, probability models, and leave you with the big ideas related to this. And it's an important idea because classification problems are probably among the most common sorts of problems that we have in the realm of data science or machine learning or predictive modeling, even in data analysis. And I've thrown up there just a few examples of those. But a way to think of a classification model is essentially any time that you're trying to classify an outcome that has a categorical sort of outcome. So is this spam or is it not? Is this network login fraudulent? Has someone stolen this theft? Does this DNA match or not? Does this face go with this person? Any of those sorts of things. Is this person going to cancel their mobile phone or not? So those are all of the, just a sample of a lot of the sorts of problems that we try to identify with classification problems. Generally, it's a binary outcome. So a yes or a no or a good or a bad or an up or a down, but it doesn't have to be. Probably 20% of the problems, in my experience anyway, that I've come across have more than one outcome. But generally speaking, binary is the one that's most common. It gives you a little more flexibility often. And most problems ultimately can be reduced down to a yes or a no, a good or a bad sort of outcome. As I'm going through, feel free to ask any questions, ask me to pause or clarify things if that's needed. And again, if my audio does get scrambled again, let me know. So there is a new disease and spreading in Canada. This one is less known, or you may have heard less about this. There's the obvious one that we read about every day in the newspaper, but this particular one is BORD 20. And we started to discover it in the spring of 2020. And current test for it, so we can test for it, we can identify it, but it's expensive, about $5,000. It's very time consuming. It takes about 5 weeks for the test to be completed, but it is a definitive test as well. We know for sure whether or not someone is suffering from BORD. But it would be beneficial, of course, to have something that's cheaper, faster, that's able to still help us identify and zero in on this. And this is the sort of problem that you're hearing a lot of from medical authorities these days with the COVID issue, wanting a quick, reliable test. So thankfully for BORD 20, and I should hasten to add that I made sure that all of the data that I'm going to be using is data that I've created. I've made up this particular disease to hopefully have a little bit of fun even in the midst of all of this. We can still smile, I hope. And but also, I don't in any way want anything that I'm presenting to be taken as medical advice. I'm not a medical professional. This is just the mathematics and the science behind some of what they're doing. So with that in mind, they have a new test. So recall, for BORD, for the old test for BORD, it was expensive. It was $5,000. The new test only costs us $1. It's fast. You get a result in 5 minutes. And it's got a 99% accuracy rate. So it's not 100%, but it's pretty close. So you might think it's awesome. You might think that that really does the ticket and it's perfect. This will help us very quickly identify everyone. In fact, we can roll this out to everyone and find out exactly what the base rate of this disease is amongst all the population. But is it any good? Well, let's take a little bit of time and try to find out. So before we do that, here's a few things that I want to just remind you. This will be review for some, and it may be somewhat new for others. But there's a lot of ways to evaluate a classification model. Lift charts, ROC curves, trade-offs between specificity and sensitivity. There's a whole gamut of methods of doing this. And of course, depending on the algorithm itself, there are a number of ways specific to the algorithm of evaluating how good a model is or a classifier is. But confusion matrices are probably the most common ones. They have their roots in quality assurance and even farther back than that, actually. And one of the excellent things about confusion matrices is they're what I would call algorithmically agnostic, meaning they're applicable regardless of how you've classified things. So if you've used logistic regression, if you've used a naive Bayesian classifier, or if you flipped a coin, regardless of how you've classified things, a confusion matrix is a way of evaluating the outcome, that regardless of what the underlying mathematical algorithm that you've applied is. So here's what we see with this particular disease, board 20. So let me just walk you through what this matrix is all about. On the left-hand side, this is the actual definitive test. So we had a pool of 200 people, and we definitively knew that 100 of them were sick and 100 of them weren't. And that's what the rows are. The rows sort of represent, these are the people that our definitive test identified as sick or not sick. And then our columns represent the new test. So we assessed it using the new test, again, the quicker test, the $1 test, the one that turns around in 5 minutes. And it identified 100 people as sick and 100 people as not sick. Now, those numbers don't necessarily have to match always. In fact, normally they won't. However, for the sake of clarity and example, I've made sure that they've matched. So what we see is that of all the 100 people who were assessed as sick, 99 of them actually were sick. And this is what we would call our sort of true positives. So our true positives are the one that we assessed with our new test as sick, and they actually were sick. And that's sort of in the upper left-hand corner. In the lower left-hand corner, we have those that we've assessed as not sick. So we've identified them as not sick, and they actually weren't sick. They actually didn't have the disease. And similarly, that's 99 of those people that we identified as not sick actually weren't. In the upper right-hand corner, we see that we have, there is one person that we identified as not sick who actually was sick. So this is a false positive, or a type 1 error, often is what it's known as. And in the lower left-hand corner, you've got a type 2 error, which is, again, those who are sort of false negatives. I reversed those. I apologize. The lower left is the false positives. The upper right is the false negatives. Basically, those that we've said are not sick, but they actually are. And so your accuracy is 99%, which is basically the total of your true positives, your true negatives, divided by 200 gives you 99%. And there are other measures that we could calculate using confusion matrices, sensitivity and specificity and those sorts of things. But for now, we'll just look at the overall accuracy of the test. So you think, okay, 99% accurate test. So I get the test, I get the take the board 20 test at home, and I test positive. So I'm 99% likely to have bored. That's the conclusion that I draw. If anyone does, this is a little disconcerting not being able to see anyone or see reactions. Hopefully some people are laughing at some of the jokes, but that 99% is not actually true. And maybe you're 99% likely to have it. So Thomas Bayes was a famous mathematician. He came up with a theorem, and his theorem gives us some guidance in this. So before I can really tell you about Bayes' theorem in detail, I need you to just remember a couple of things from any sort of probability classes that you've taken. So at the top, P at X is the probability of event X happening. So, the probability X being sick. X might be the probability that something is spam email, the probability that something is fraudulent, those sorts of things. Probability P of X and Y is the probability of both events, the conjoint probabilities of both X and Y happening. So for example, in weather forecasting, you might say the probability of it being event X might be it is a sunny day, and Y is but it rains in the evening. Those are two events, and those can both occur. Okay, and then the next one down is what we call the probability, conditional probability. So this is the probability of X happening given that Y has occurred. So for example, you might have something, the probability that it will rain this afternoon, given that it is very cloudy right now. Or, the probability that it will rain this afternoon, given that it's very sunny right now. So those are conditional probabilities. And intuitively, I think that makes sense to most of us. If it's cloudy this morning, we think it's more likely to rain. And if it's not cloudy this morning, we think it's less likely to rain. And we make those decisions every time we leave the house. Back in the days when we did leave our houses, we'd look out the window and, oh, what does it look like? Does it look like rain? That's essentially what we're assessing, is a conditional probability. Given what I see, what's the probability that it's going to rain and that I'll need an umbrella or a coat? Everyone clear on that? Okay, so let's look at our example. Let's take a total population of 10,000 people. And in that population, only 1% of them have bored 20. So only 1% of the population, or 100 people, are sick. And 99% of the population isn't sick. 99% of the population doesn't have bored. And so if we look down at it, if we tested those 100 people, 99% of them would test positive, and 1% of them would test negative. Similarly, amongst those who are not sick, 99% of them, or 9,801, would test negative, and 1% of them would test positive, or 99. So that just sort of is a flow through from what we've seen on the previous, that's just a flow through from what we've seen on the previous slide with the accuracy of the test, or what we're likely to see. In other words, 99 out of 100 people who are actually sick test positive, 99 out of 100 people who are not sick test negative. So what we're interested in is, what is the probability that we are sick given that we've tested positive? Now up above, and I didn't describe this, was Bayes' theorem. So Bayes' theorem basically states, well, not basically, it does state that the probability of Y given X is equal to the probability of X given Y times the probability of Y divided by the overall probability or incidence of X. So that's Bayes' theorem. Sometimes it's called Bayes' law, but normally that's just in England they call it Bayes' law. Here we call it Bayes' theorem. So if we apply that down below, what we see is that the probability that I am sick, given that I've tested positive, is equal to the probability that I've tested positive, given that I am sick, which is 99, times the probability that I'm sick, and that's the 1%, right? 1% of the population is sick overall. So that's where that 1% comes from on the numerator. In the denominator, we calculate the overall probability that I would have tested positive. So if I'm actually sick, then the probability I would have tested positive is 99. So 99% times the 0.01% of people who are sick, plus the people who've tested positive who weren't sick, 1% of those, times the overall 99. And calculating that all through, what I see is the probability that I am sick, given that I tested positive, is only 50%. If we flipped this around, in fact, and we said, well, what's the probability that I'm sick, given that I tested negative, right? So if I tested negative, what's the probability that I'm sick? And if we did these same calculations, what we'd see is that the probability I was sick, given that I tested negative, would be 0.51%. So much more accurate, if you will, than the initial test design would suggest. So what is going on? This is bonkers. Is it 99 or is it 50? So which is it? Well, the answer is it really kind of depends. What you'll see is that on this slide, the underlying incidence of the disease amongst the population is a critical piece of information. If we change that 1%, if say 50% of the population was sick, then all of those numbers would change. If 85% of the population were sick, then all of those probabilities would change. Which is why we're hearing a lot from medical professionals talking about how important it is to know what the overall incidence of COVID-19 is amongst the population. And not only does that help with the overall modeling, of course, and figuring out when we'll hit the peak and all of those logistic planning issues, but it also is critical information to help assess test results that are coming back, because very few medical tests are 100% accurate. Everyone more or less there with this so far? It's a somewhat counterintuitive result that sometimes surprises people when they first see it. Okay, let's move on. So many of you, if we were here in a classroom, I'd ask you to hold up your hands and all being excellent students. I'm sure you would. But all of us, I'm sure, all of us, I'm sure, have been to the doctor, and the doctor will ask us a bunch of questions. The doctor will ask us questions even before they do minimal tests, like blood tests for anything, testing our blood pressure and all of those other things, and trying to diagnose us with any sort of a thing. Even before they run the test, they're asking us questions. And it's more than just a pre-screening. So often we do that. Often they do it to decide, well, is it worth testing someone with this? So for example, if testing is very expensive, so in this example with board 20, where the testing is costs $5,000, you only want to test people who have a high likelihood of actually needing it. Similarly, now, if you went to your doctor and you asked to be tested for COVID-19, but you're showing none of the symptoms, you've got none of the risk factors, you've been staying at home for the past 2 months and haven't poked your nose outside and haven't had contact with anyone, he's unlikely to give you the test. Not only though, because it is a waste of resources, but in some ways, even more importantly, it modifies the general likelihood of you having that disease. So if we look back on the previous slide and we saw how the overall incidence was 1% of the population having the disease, if we can create a subset of that population with pre-screening to elevate that, that incidence, then we have more confidence in the overall test results. That makes sense to everyone? Also, the reason, the previous slide is also the reason why, if any of you have ever had or know anyone who's had medical scares or tested positive for potential severe medical issues, they never rely on the first test. Usually they'll do a first quick and easy test, and they'll tell you to not panic, to relax. They want to do more tests and so on. And this is absolutely why, because just because you tested positive and it's a 99% accurate test does not mean that there's a 99% chance you have it. It could be substantially lower. So that's kind of the background and the logic with some of these pre-screening questions. So let's look at a few of these for board 20. So one example of board 20 is, do you live alone? So people who live alone are much more likely to suffer from bored. People who do not have reliable internet are much more likely to be bored. People who do have reliable internet, much less likely to be bored. And again, somewhat paradoxically, with this particular affliction, the affliction of bored, it tends to be related to age, but those under the age of 20 tend to suffer from it to a greater degree than those older ones. In fact, some of the studies with board 20 have found that that seniors who knit and have lots of pictures of their grandchildren are almost completely immune to bored. But it does seem to be the young who tend to be bored a lot more. So those are the three questions that we're going to be using as we evaluate bored or do this pre-screening of bored. Now, what I've described, I should, before we go further, what I've described on the previous page is a super simple example of what we would call a Bayesian probability model. Normally, it's used as a classifier to classify as sick or not. And so what I'm going to show you with the classifications doesn't actually yield true probabilities, but it's much more used for classification. And I'll talk a little bit more about that later for those who are interested. Okay, so here's an example. So what we see is, and the way to read this chart is those who have reliable internet. So 53% of people, so if you look at the 1, 2, 3rd column, which says S and NS, that stands for sick and not sick. So 53% of the overall population has reliable internet, 47% doesn't. Of those who have reliable internet, only 10% of them have bored. Sorry, let me word that another way. Of those who are sick, 10% of them have reliable internet and 90% of them do not. Of those who are not sick, 96% of them have reliable internet and 4% of them do not. So that's the way to read it. Each of those columns should add up to 100, right? So again, similarly to the live alone, 85% of those who are sick live alone, 15% don't live alone, and so on. And age is another example of that. So this is a little bit. So here is how a naive Bayesian classifier works. So let's look at a particular patient. So a particular person, they have reliable internet, they live alone, and they're under 20. So they live alone and they're under 20, so that puts them at a greater risk of it, but they have reliable internet, so that puts them at a lesser risk of it. So as we look at this, we see that the probability of them being sick, given that they have reliable internet, they live alone, and they're under 20. That's what we're trying to figure out. We're trying to figure out what is the probability that this person is sick. So we multiply the probability of being sick overall times the probability of having internet, being alone, and under 20. And this is the probability overall, or sorry, given that you're sick, right? So the probability that you have internet, you live alone, and you're under 20, given that you're sick. And we divide all that by the overall incidence of that combination of having reliable internet, living alone, and being under the age of 20. And we just sub in those numbers. So for probability of sick, I've put in 0.5. Why did I choose 0.5? I chose that because the data above, that was the incident in that sample that we took. So it doesn't bear on the overall population, but it does bear on this particular one. And you may say, well, that's an awful lot lower or higher than the one we were using in the previous example. Sorry, Norbert, you're a little garbled.
Oh, I'm sorry. I pressed the wrong button. I'm just still listening.
Oh,
I'll just mute myself again. Okay.
Okay, thanks. Okay. And hopefully I'm still clear. I just bumped one of my wires. Right. So I've taken that 50%, and that's because when I was generating those ratios of likelihood above, that was the sample that we looked at. So this was the original test sample from when they were developing the test from a few slides back where we had those 200 people. But then we multiply, we see that the probability of having reliable internet, given that you're sick, is 10%. So that's the 10. And we see the probability of living alone, given that you're sick, is 85. So that's the 85. And the probability of being under 20, given that you're sick, is 53. So that's the numerator, and we multiply those together. The denominator, we're just multiplying the overall incidences. So reliable internet is 53, living alone is 45, and 30% of people are under 20. Calculate that all through, and we end up with 0.31. So you might say to yourself, okay, wow, so there's a 31% chance that they're sick, which means that there's a 69% that they're not sick. You might think that, but you would be incorrect. Yet again, it is counterintuitive. So if we look down and we do the calculation for probability of not sick, given that you have reliable internet, you live alone, and you're under the age of 20, and we work out all of those numbers, what we see is that it's 0.0235, which again is a somewhat counterintuitive number. Now, in a naive, and I'll talk about why that is. In a naive Bayesian classifier, we really compare those two outcomes, and we take which one is higher. In other words, which one is more likely. And in this case, we'd say it's more likely that this person is sick than not sick. So, but you would think they need to add up to 1, right? Those of you who remember your probability theory. So why isn't that the case? And the answer is because it's called naive Bayesian for it's called naive Bayesian for a reason. And the reason, one of the reasons anyway, that is called naive Bayesian classification is that Bayes' theorem assumes independence of events, or at least calculating. I should clarify that. The way we've calculated the conditional probability assumes the independence of it. Bayes' theorem itself doesn't assume independence. So I apologize, that is not an entirely factual statement, that first bullet point. The way we've calculated the conditional probabilities on the previous slides does assume independence, but Bayes' theorem does not. So let's go back up. So notice how I calculated the probability of the internet, having the internet, living alone, and being under 20, given that you're sick. I just multiplied those ratios together. Now, this is something that you're only allowed to do if having internet, living alone, and being under the age of 20 are completely independent. In other words, they're not related to each other at all. That's the naive part of the naive Bayesian classifiers. We assume that all three of those observations are completely independent. And we know they're not. We know that in real life they're not. And in this example, we know that they're not. People under 20, there would be a strong correlation, I would suspect, between having a reliable internet connection or not. So doing that conditional probability calculation, we are assuming that they're all independent, and they're not. And another example is, this is a classic example, actually. If you say that you like peanut butter and you also like tea, then a naive Bayesian classifier would decide that you like peanut butter tea. Or if you like ketchup and you like coffee, a naive Bayesian classifier will declare that you probably like ketchup flavored coffee. And that might be true, but probably not. So there's a lot of mathematics behind how we get around these things and how we use it. But that's the naive part of the Bayesian classification. There are people working on Bayesian classification, but they are much, much, much more complicated problems to solve. It's a whole sub-branch of statistics that people specialize in. Generally speaking, what they'll try to do normally is to approximate the true probabilities, though. So in that previous one, we had the 0.31 and the 0.02. So generally speaking, we'll try to get an approximation of what the probabilities are just by dividing the one by the others. So in this case, we'd say, well, our probability of sick, given that we're living with internet and alone, that's the 0.31 divided by the 0.31 plus the 0.02, the two numbers from previous, they give us a 93% chance that we're unwell. And again, this is an approximation. And because it's a naive Bayesian classifier, we even have a hard time putting boundaries around exactly how confident we are in that 93. But we'll take that 93 for now. So what we've done a pre-screen. We've said, okay, this person has reliable internet, they live alone, and they're under 20. So we think that based on those three pieces of information alone, that population has a 93% incidence of being bored. So recall, this was our calculation that we did to look at our test results. And now we have 99, which so that's the percent who are tested positive, given that we're sick, is 99%, times the probability of being sick. In this case, it's the 93 from the previous slide. And then our probability of testing positive, well, again, it's 99 times the 93, testing positive if we're sick, and testing positive if we're not sick is a 0.01 times the probability of being not sick. Again, the 07 is just a 1 minus the 0.93 from the previous slide. So we've calculated, we've essentially pre-screened, and we've changed the rules of the game. We've changed that underlying base incidence of the disease amongst the population because we're looking at this particular subset. And what we find out is now the probability, we test this person positive, they test positive for the test, and now we are 99.92% certain that they actually have bored 20. So by pre-screening, that's what we've done. We've moved from a 50% certainty to a 99.92% certainty, assuming all of those probabilities that I've talked about. But certainly it's much higher than 50%. We're much more confident that it is, we're much, much more confident now that that test result really is indicative of someone actually having the disease than we were previously. So the pre-screening, as I say, not only restricts the testing to those who really need it, it also dramatically improves our ability to properly interpret the results of the individual test. Any questions on that? I know that was a little hard slogging, and it can sometimes be difficult just sort of looking at a screen and doing this. It's sometimes easier to sort of have this written out and so on. So you might say, if this is so useful, why don't we use it everywhere? Well, not so fast. Because as any of us who have seen Spider-Man movies know, with great power comes great responsibility. So naive Bayesian classification is probably the most common classification algorithm uh, in use today, particularly in machine learning applications, and particularly in ones where we're doing real-time calculations, because it is fast. It's super fast. And it performs really well in multi-class prediction. Logistic regression and other sorts of classifiers don't tend to work better with binary outcomes. Naive Bayesian has a multi-class outcome, which and works much better with those than a lot of other tools that we have at our disposal. And it really is just like greased lightning. If the assumption of independence holds, the classifier, it does work really, really well. The degree to which that those input variables are dependent on each other, the more dependent they are on each other, or the more independence is violated, the less well naive Bayesian tends to perform, which is just sort of intuitive, but it does sort of also indicate when you're building models or classifiers using this, how important it is to think about your input data set, to use some sort of, again, pre-screening or data dimension reduction techniques that are very sensible to minimize that degree of dependence when it first goes through the algorithm. Reasons not to use it. It's a bad estimator. And again, what I mean by that is that those probability calculations that we did on the previous few slides, you can't hang your hat on those. And there aren't even really many tools to put some boundaries around it, you know, plus or minus 5% or anything. They really are just a rough approximation. So it's an excellent classifier. So if you're trying to decide, is this likely to be spam or not? Excellent for that. If you're trying to figure out, this is 95% likely to be spam or not, it's not so good. So that's the difference. Again, it's naive. If you don't have independent predictors, it's a really problem. The other issue with it is that with highly dimensional data, if you think back to that slide from a number of slides back when I was showing those 3 pre-screening questions, and each of those just had a binary outcome. If you're trying to, if you imagine a much larger data set with many more variables and many more possible values of variables. So for example, instead of having age less than 20, if I had age broken up into groups of 5, well, it's quite possible that in that chart that I would end up with cells where there's no one. There's no one who is all of those things. There's no one who has, you know, a reliable internet, is over 80, and doesn't live alone. There may be no one like that. There may be no observations in that area, which means you end up with the classification doesn't work. So you need population. You need values in each one of those particular fields of that table, which you might think, especially in the era of big data, that that's not a problem. But big data in some ways is a bit of a misnomer, because even if you look at enormously large data sets, sparse data is a pretty common feature of a lot of it. So we will see, so for example, if you have a real-time feed, for example, of a GPS positioning, so you've got a watch or your phone. Well, many of those tools are having a data feed of 4 times per second of what the renewed position is. And so if you were to look at a data stream, even for just one day, say for yourself, and you were to look at the change in position, right? You're changing your change in position per second. There would be times of the day when you're walking around or you're driving in a vehicle. Back in those days when we did those such things, there'd be data there. But for much of the day, you're sitting in one spot. So that data is going to be very sparse. There's going to be just zeros there if you're trying to calculate, velocity or movement. So that's another area in which it can be pretty challenging. I'm not going to talk about implementations. Those are easy to look up if you're interested. It's really simple to program this stuff. Most major languages and tools have naive Bayesian packages. In fact, in the case of Python and R, there are several that you can choose from. But even if you wanted to code this stuff from scratch, it's pretty straightforward and pretty intuitive to use it. So there is a whirlwind introduction to naive Bayesian classification. Again, overly simplifying certain aspects of it, but hopefully you're left with the big ideas of what's behind it. And I'm certainly happy to take any questions, but in the absence of those, I'll just thank you for your kind attention. So I'll open it up for any questions or comments if anyone would like to share. Absolutely, Mark. That's 100% correct. Excellent for yes or no. Or yes, no, maybe, doesn't need to be binary. But yes, percentage of accuracy, very, very hard to dial in on. Any other questions for anyone? Absolutely. Absolutely. That was actually one of the things that you may have noticed on one of my first slides. Yeah, this is the sort of tool that can easily be used in an admissions department. I don't know if Conestoga uses it at all, but absolutely applications to assess student success based on their application. Looking at historic outcomes to then apply this to see what is the likelihood of them successfully completing the program. Oh, yeah, great question. Yeah, in real problems, there's often more than 3 factors. It really depends on the length of your data set. In general, this is a rough rule of thumb. In each one of those squares in that field, you want to make sure that you've got enough data that you have at least 10 in each one of those fields. But that's a rough sort of rule of thumb. So for example, if you're dealing with 50 variables, you'd want several thousands of observations to make sure that you've got sufficient population in each one of those boxes, if you will, of the matrix. That answer the question? Listen, thanks so much, everyone, for taking time out of your day. I know it's final week is really busy for all of us. I don't, my students don't have an exam till tomorrow, so I'm not doing any marking yet, but I do appreciate you taking the time. Do appreciate you taking your time. Hopefully it was worth the 45 minutes of your time. And always I'm available. Just shoot me an email if you've got any more follow-up questions and you want to learn more about this stuff.
Thank you, David.
You're welcome.
Yeah, thank you so much, David. Much appreciated, and thank you to everyone who has presented in this short series of Lunch and Learns. Seeing as it's exam week, I really appreciate the great turnout. Now, for future weeks, I don't have anything booked yet, but please, if you have any ideas on things you'd like to present going forward, I still have a bit of a list for when we have these up and running once the grading is all taken care of. So thanks so much, everyone. And again, thank you, David.
You're welcome. Thanks. Have a great afternoon, everyone.